Picture the biggest moment of a World Cup match. A goal goes in. Across the planet, tens of millions of people who were half watching on their phones jump straight back to the live stream, all in the same second. That single second is the hardest problem in this whole video. Streaming video to one person is a solved problem. Streaming the same video to 100 million people, all wanting the same few seconds at the same moment, breaks assumptions that work fine at small scale. This video is about the architecture that survives that moment. Here's what we'll cover: why a single origin server collapses the instant everyone seeks back to live, why routing everyone through one region isn't enough, why your video quality drops at the exact worst moment, and how many edge servers 100 million viewers actually needs, and how you get them ready before kickoff, not after. Here's what actually happens at the goal. Viewers aren't spread out anymore. A huge share of them do the exact same thing at the exact same moment, jump to the live edge of the stream. To a server, that looks like one enormous request landing all at once, not steady traffic. In the naive setup, every viewer's player talks straight to one origin server for every piece of video. That's fine for 1,000 viewers. At 100 million, the origin gets the same request for the same few seconds of footage from millions of players in the same instant. It cannot keep up, and it starts timing out. Break down why this fails. There's one origin server. There are millions of players, all asking for the same handful of seconds of footage. The origin's connection queue fills up, and requests start timing out, not because the video is broken, but because one machine can't answer millions of identical questions at once. The fix is a content delivery network, or CDN, a layer of servers spread around the world, sitting between the origin and the viewer. The first request for a video segment goes to the origin and gets cached at the nearest edge server. Every request after that for that same segment gets served straight from the edge. The origin is asked once. The edge answers everyone else. Here's the mechanic in plain terms. The very first request for a segment is a cache miss. The edge has to fetch it from the origin. Every request after that for that exact same segment is a cache hit, served straight from the edge's memory in microseconds. During a goal, almost every request is a cache hit. The origin barely notices the spike. Edge caching solves the origin problem, but it creates a new one. If every viewer everywhere is routed through one CDN provider, or one region of that provider, you've just moved the single point of failure. You haven't removed it. Say every viewer in Asia and Africa gets routed to the same set of edge servers in one region. If that region's network gets congested, or the CDN provider itself fails, every one of those viewers buffers at the same time, even though the rest of the world is fine. The fix has two parts. First, use more than one CDN provider so one company's outage can't take the whole stream down. Second, use Anycast, a routing trick where the same address is announced from many locations at once, and the network automatically sends each viewer to the nearest one. Combine both, and a struggling region routes around itself. This happens continuously, not just when something breaks. Every edge is health checked every few seconds. The moment one starts struggling, new requests get steered somewhere healthier. A well-run multi-CDN setup sheds load off a struggling edge before it fails completely. Most viewers never know it happened. Even with caching and multi-CDN routing solved, there's a third problem. At the exact moment of the goal, the moment everyone cares most, video quality often drops. That's not a bug. It's a deliberate trade-off, and it's worth understanding why. At the goal, every player near a given edge asks for video at the same moment, the same spike we've already covered. Even with caching and multi-CDN in place, the connection between that edge and your specific device can get congested. Your player is now watching its own buffer drain, and it has exactly one choice to make. The fix is called adaptive bitrate. The same video gets encoded at several quality levels, from very sharp down to very light, called a bitrate ladder. Every few seconds, your player checks how much its buffer is filling up and requests whichever level it can sustain without stopping. When the network gets tight, the picture gets softer on purpose. That's the trade the whole system is built to make. Keep the video playing, even if it means it doesn't look its best. This is why it feels like the worst possible timing, because it is. The number of people watching peaks in that second. The strain on every edge and network link peaks in that second. And viewer attention, how much a freeze would annoy someone, also peaks in that second. Quality doesn't drop randomly. It drops exactly when the system is under the most pressure, which happens to be exactly when you're watching closest. We've covered caching, multi-CDN routing, and adaptive bitrate. There's one question left, and it's the one that decides whether all of this holds up on the day. How much edge capacity do you actually need, and when do you need it ready by? The exact numbers vary by provider, but the shape of the problem doesn't. One edge node comfortably handles a few thousand concurrent viewers. To reach 100 million, you need that same ratio repeated across many thousands of edge nodes, spread across the planet. The hard part was never the arithmetic. It's having that many nodes standing by, warmed up, before the match even starts. Auto-scaling, adding capacity automatically as load rises, works great for traffic that ramps up over minutes. It does not work for a spike that arrives in 1 second. A newly spun up edge node also starts with an empty cache, so its first minute would be full of slow cache misses, right when speed matters most. The fix is to pre-warm. Provision the extra capacity ahead of time and load it with the content you expect to be popular hours before kickoff, not react after the spike already hit. In practice, this is a 4-step playbook. Forecast the spike using the event calendar. You know a World Cup match is happening, so you don't have to guess. Pre-provision the extra edge capacity well before kickoff. Pre-warm the cache by pushing the segments you expect to be most requested out to the edges in advance. And once the peak passes, scale back down gradually, not all at once, since the tail of a big event still draws a crowd. Put it all together, and here's what happens every time someone hits play. Anycast routes them to the nearest healthy edge. That edge almost always has the segment cached already, so it serves it immediately. Their player picks the highest quality it can sustain without stalling. And if that edge is getting close to capacity, new viewers get quietly shifted to the next pre-warmed edge nearby. None of it is one trick, it's 4 systems, each covering for what the others can't. Every one of these problems traces back to the same root cause, a synchronized spike, not a gradual one. The naive setup, one origin, one region, reactive scaling, melts the second it happens. The setup we've walked through, cached at the edge, spread across multiple CDNs, pre-warmed ahead of time, is built to already be ready when it happens. So to recap, cache video at the edge, so the origin answers each segment once instead of 1,000,000 times. Spread across multiple CDNs with Anycast routing, so one bad region can't take the whole stream down. Let bitrate adapt, so the player protects continuity over resolution. And pre-warm your capacity before the event starts, because reactive scaling is always a step too slow for a spike that arrives in 1 second. If this changed how you think about what at scale actually means, subscribe. Every video here breaks down one system senior engineers understand instinctively and walks through exactly how it works.